Welcome back. In this video, we will continue with Chapter 17, Electric Potential. We've covered two topics so far, electric potential energy and electric potential difference. And we talked about the relation between electric potential and electric field, and potential is a scalar and field is a vector. Those topics, I think, were somewhat abstract. I think they'll become more clear as we move through the chapter, especially with our next topic, equipotential lines and surfaces. And we'll talk to electric potential due to point charges, and then some new topics, capacitance, dielectrics, and storage of electric energy. I don't think we'll get to these last two. All right, so equipotential lines. An equipotential is a line or surface over which the potential is constant. So our potential, remember, we can measure in volts. And we represent it with the symbol V. And we have our little equation for potential up there on the right, that it's the energy per unit charge as a reminder. But that's somewhat abstract. I think this becomes easier if we look at a diagram here. So here we have what should be a familiar image. We have a positively charged plate to the left, a negatively charged plate to the right. Electric field goes from positive to negative, from left to right, as shown by the red lines. And what we've added now are these green lines, and those are equipotential lines. Let me skip down here to the bottom. I'll go through all of these. But the surface of a conductor is an equipotential. So this positive plate is, say, plus 20 volts, and the negative plate is 0 volts. The whole surface of the positive plate is 20 volts here. This whole surface is 0, and so we have a decrease in potential as we move down an electric field line. And if we have a uniform electric field, we just get nice parallel equipotential lines. So here's 15 volts, 10 volts of potential, 5 volts of potential, and 0 volts. All right, what did I miss here? We have electric field lines are always perpendicular to the equipotentials. This might help us to understand that concept of why the electric field lines can't cross. You can think about that as we move along. And the electric field lines always point in the direction of decreasing potential. And while I could say that in the last video, it's much easier to see it here now that we have different potential lines. We can see the electric field as we move from left to right, we're crossing different equipotential lines. And as we go down the electric field line, the potential decreases. So let's look at some other geometries. If we just looked at a point charge, the equipotential for a point charge, again, the equipotential lines are perpendicular to our electric field lines, so we can draw it with the knowledge we have. We can draw it fairly readily. It will be concentric circles. How far apart the circles are, we'll understand better shortly. But we can see the equipotential lines are concentric circles around a positive point charge where the electric field lines go radially outward. For a negative charge, the electric field lines would go radially inward, and our pattern for equipotential lines would look similar, but they'd have negative potential instead of positive potential, and we'll see that. All right, what about more complicated configurations with multiple charges? If we have a positive and negative charge, the red lines again are our electric field lines. We've seen those before, and now the equipotential lines have been added. So if you wanted to add some numbers to these, the first one I can tell you is that right up the middle, the equipotential is 0. You could figure that out. You have positive potential around a positive charge and negative potential around a negative charge. And right in the middle, if they're of equal charge, right in the middle, the equipotential is 0. So from here, you could be going up to, say, plus 2 volts, plus 4 volts, plus 6, plus 8, plus 10 volts as we approach the positive charge. And here it might be minus 2, 4, 6, 8, 10 volts as we approach the negative charge. And you can see right between the two charges, those equipotential lines are equally spaced. But if we go on the opposite side where the field lines are spreading out, the distance between the equipotential lines is increasing with a pattern more similar to that of the point charge in the previous slide. All right, one more. I pulled this slide from online from University of Washington, and it shows you for two positive charges, the purplish lines going radially outward are electric field lines, and you can see they don't cross. And if you drew perpendiculars to those, you could come up with your equipotential lines as we see here. All right, so let's go back to a conceptual question. How much work do you think is required to move a charge at constant speed along an equipotential line or surface. So let's say we had an electron here. We just wanted to move it along this green line, 15 volts, over to this point. How much work would be required? Well, I think it's helpful if we want to think about this question to go back and think again about gravitational potential, because our concepts there apply and it might be easier to relate. So here is a picture of, say, a topographic map, and equipotential lines at equal potential. For electric potential, it was those voltage lines. For gravity, it's topography lines, pretty much. So you might recall, if we move along a topography line and we don't go up or down, we don't do any work against gravity, we don't do any work. That's if we don't accelerate. So if we're going at constant speed and we stay on a flat surface, from a physics point of view, we do no work. You could review that in Chapter 6. The same is true here. And if you move a charge along an equipotential line, from a physics point of view, you have done no work. You have to move the charge along an electric field line in the direction of the electric field. You have to change your potential in order to do work. All right. A new unit of energy we can introduce at this point is the electron volt. Remember, we have this work energy principle. When we talk about work, we can also talk about energy. And 1 electron volt is the energy gained by moving an electron through a potential difference of 1 volt. And that corresponds to 1.602 times 10 to the minus 19 joules. And that may look like a familiar quantity because it is the charge on 1 electron or 1 proton. But we're moving that electron or proton through a potential difference of 1 volt. That gives us a unit of energy of an electron volt. So we now have a conversion factor to go between joules and electron volts if we need it. Let's consider the electric potential due to a point charge. And if we were in a calculus-based class, we could derive this with calculus, but in our algebra-based class, we are given the equation. So the potential for a point charge, and once again, the book does not give us a subscript that says point charge, but I recommend if I were writing down equations, I would write that down. The potential of a point charge is K, that constant, Q, the amount of charge, divided by R, your radial distance away from the charge. And you can write K in terms of epsilon 0 as well. So these two equations are equivalent, since K equals 1 over 4 pi epsilon 0. For this work, I tend to use the upper equation because it's simpler. If you're remembering from Chapter 16, we had the electric field of a point charge, and I've written that up here in the upper right just for comparison. That was KQ over R squared. Many standardized tests would like to test on either electric field of a point charge or electric potential of a point charge. So if you have to memorize some formulas, these are some good ones to commit to memory. And so our electric field is KQ over R squared, potential is KQ over R. So electric field decreases as radial distance squared, potential just decreases as 1 over R. Okay, I might add that these green lines are placed at correct distances for uniform decreases. Could be at, say, 2 volt, go the other way, 10 volts, 8 volts, 6 volts, 4 volts of potential from a certain strength charge. So that the equipotential lines do get farther apart as you go further from the charge for an equal drop in potential. So we can look at that visually here. For a positive charge, as we move radially away from the charge, so this is a plot of potential on the y-axis and our radial distance on the x-axis. As we move radially away from the charge, the potential drops as 1 over r. For a negative charge, we have negative potential. And as we move away, the magnitude drops, but we're going from more negative to less negative. But the magnitude drops in a mirror image for a positive potential. So our magnitude drops as we move radially away. And they're just following that equation. Potential is KQ over R. So at this point, it's a good opportunity to review our basic concepts one more time. Electric field goes from radially outward from a positive charge, radially inward to a negative charge. If you have a positive negative plate, it goes uniformly across from positive to negative. While the potential is going to be lines perpendicular to our electric field. The electric field lines will point in a direction of decreasing potential. And At this point, we can come back and revisit that idea of potential energy. So this is the image we started with in chapter 17, and we started with a positive charge. And I think now you can see why, if you're near the positive plate, whether you are a positive or negative charge, that is a region of high potential because that's your voltage. For this example, for instance, anywhere along here is 20 volts. Anywhere along the right-hand plate is 0 volts. So anytime you're up an electric field line, you have relatively high potential, regardless of the charge you place there. Close to the positive plate is a region of high potential, whether you are a positive charge or a negative charge. Near the negative plate is a region of relatively low potential. What about potential energy? Again, it's good to think about the concept that likes repel. So you place a positive charge near the positive plate, there's going to be a strong repulsion there. That's a region of high potential energy. You place a negative charge near the positive plate, it would be attracted to the positive plate, so that's a region of relatively low potential energy. In contrast, you place a positive charge near the negative plate, that's a region for the positive charge of relatively low potential energy. It's attracted to the negative plate. You place a negative charge near the negative plate, likes repel, and that's an area of high potential energy. And actually this concept we've had before as well. Using potentials instead of fields can make problem solving easier because potential is a scalar quantity, whereas the electric field is a vector. All right, let's try a problem. A point charge Q creates an electric potential of plus 125 volts at a distance of 15 centimeters. What is Q? How many coulombs of charge do we have there? I've got a little diagram up here showing myself a little positive charge. I've got my electric field lines going radially outward. I've got my equipotential lines. So I have an image of what's going on. And we know at a distance of 15 centimeters, I can arbitrarily say that's the second equipotential line out, the Q creates a charge of plus 125 volts. Oh, I already applied the knowledge, by the way, that's positive. If it's positive potential, I know it's a positive charge. If we'd known it was negative 125 volts, we'd know we were in the vicinity of a negative charge. You can look back at the last few slides and reinforce that idea. All right, we have an equation that relates potential to charge and radial distance, and that's exactly what I need for this problem. I'm asked to solve for Q, so I can rearrange for that, and I'll write down what my knowns are. Be a little careful in this case. So my potential is plus 125 volts at a radius of 15 centimeters. I always convert to meters so that units will cancel easily. So that's 0.15 meters. And my constant here is 8.988 times 10 to the 9 Newton meters squared per Coulomb squared. All right, so now I can rearrange my equation, solve for Q, so cross multiply and divide, and I get Q equals VR over K. I can just plug in my values, and once again, quantitatively, these problems don't tend to be challenging. It tends to be the concepts that are harder. So I plug in my values and get 2.09 times 10 to the minus 9. Since I'm solving for an amount of charge, I can assume my unit is coulombs, and that's what I've shown here, but I can also derive that. So units check. A unit of a volt is a joule per coulomb, and I'm pulling back from last semester, a joule is a Newton times a meter. And the units I had up here was a volt times a meter over Newton meter squared per Coulomb squared. So I've written all that here. I replace my volt with a joule per coulomb in the first swap here. And then over here I replace my joule with a Newton meter. And once I do that, all my units cancel except a per coulomb in the denominator, which becomes coulombs, and my units are good. I've thrown in a conceptual question here. There are a number of good misconceptual questions in your textbook at the end of this chapter. I pulled one out of there. Two identical positive charges are placed near each other at a point halfway between the charges. And what this question does is make sure you understand the difference between electric field and electric potential. In order to answer this, I'm going to pull in an image of two positive charges. So you can do it either in your head, you can pull forward this image, or you can jot it down. So we have two positive charges. The pinkish purple lines are electric field lines. The blue-green lines are potential lines in this case. And we're asked about what's happening right between the two charges, right where my arrow is resting. All right, so is the electric field 0 and potential positive? Well, this is actually a little disappointing that's the first choice, because the electric field here indeed would be 0. The electric field at this midpoint will be the sum of the electric fields from the two charges, and you could think of the electric field from one charge and the other charge pointing in opposite directions of equal magnitude, so they'd cancel, and it would indeed be 0. And the potential for a positive charge is going to be positive potential, so we'll have a positive potential at that location. Let's just check the others. The electric field is 0, we already said that. Is the potential 0? Now, again, you can think about the potential as being the sum of the potentials now from the two charges, and since they're both positive, you'll get a positive potential at that midpoint. The electric field is not 0, potential is positive. Well, we've already shown 0 and the electric field is 0 and the potential is positive, so I think we'll move on from there. All right, I actually think that's enough for one video, so I think I will stop there and we'll finish things up in a third fairly quick video. All right, see you then.